Okay, AP Calculus AB, Unit 4, Day 4, lesson. Warm up first. So go ahead and try the warm up. Pause the video. There's a little cool. The quote at the top is actually the lyrics of a song. I don't know if you guys might recognize what it is. Fixing a hole where the rain gets in, stops my mind from wandering where it will go. Anyways, you might realize the hole reference at some point as you're doing these problems. Some of them are holes, but okay, go ahead and try the warm up. And so pause it and try the warm up and then unpause it, and I'll go over the answers. Okay, assuming you've tried the problems, if we plug 2 in, we get 0 over 0, which is often caused by a hole in the graph. So we should factor the top and bottom. I mean, let's see, x minus, probably should get an x minus 2 out of it, right? I mean, you know you should be getting x minus 2 because that obviously causes 0, so it's got to be a factor. So there's the hole, and we evaluate, and we figured out what should be where the hole is. Okay. You could also do L'Hopital's rule because you show that it is 0 over 0. So you could do limit as x goes to the derivative of the top, the derivative of the bottom, and you get the same answer. So on your next test, I will make you do some problems both ways. Okay. Next one, we're approaching 2 from the left side, right? It's a one-sided limit. At first, you might just plug in and say, okay, well, this is going to be 4 over 0. Okay, so it's going to be some kind of infinity. Is it positive infinity or negative infinity? So 2 from the left would be like a 1.99999 right here. Minus 2 is going to be a negative tiny quantity, so it's going to go to negative infinity. Very large negative number. Okay, so that one's not a hole. It's a vertical asymptote. Okay, here we're going to infinity, so this is in behavior. First thing I would do is I'd say, well, if we plug infinity in here, this would be some kind of negative infinity on the top. The bottom, you know, you can multiply this all out, but it's really these first terms right here. That's the dominant term, 3x squared. So that's going to be a positive infinity. So you know you're going to get a negative answer. And you could do L'Hopital's rule. I wouldn't recommend it on this one. It would take a couple steps of it. But we're looking at the dominant terms. When we go to infinity, we can look at the dominant terms and just say, okay, well, they have the same degree, so it's going to be the ratio of the coefficients. It's going to be negative 2/3. Done. That's a fast way of doing it. I mean, you could do L'Hopital's rule. I mean, you could, I wouldn't recommend this, but this is what I've shown you guys in class where we can divide the largest denominator out of everything on the top and everything on the bottom. And I think this just really illustrates what's happening now. If we were to do that, we probably want to get the rest of this. This is minus 6, minus 5x, minus 2. Those terms I'm arguing are tiny compared to that when we plug infinity in. But this really, I think, shows how those are insignificant. So if you multiply through by 1 over x squared, you get this. Now, as x goes to infinity, you divide by infinity, that goes 0, 0, 0. This is what's left, negative 2/3. Now, I wouldn't do that work usually, but it really helps, hopefully, to clarify why we do ignore these other terms when we're going to infinity. Now, this one's going negative infinity. Now, if we plug this in and get square root of it, it's positive infinity on the top, negative infinity on the bottom. You know you are, going to get a negative answer, which is good because this is an easy problem to mess with the sign. Now, this is the dominant term, this is the dominant term. So the dominant term is really like 3x on top. over x. They have the same degree. So usually if that was the case, you would just say, oh, well, the answer is the ratio of the coefficients. It's just 3 over 1 is 3. But that contradicts what we predicted, that we'd get a negative answer. Okay, and the reason is that we should have put absolute values around this. When you take an even root, something that has variables in it that raise an even power, that negative went away and it is gone. But if we don't put these absolute values around it, it's like it's still there. So the answer is -3. Now, this is a problem that we could do L'Hopital's rule on, but I feel like it involves some derivative rules we haven't really discussed yet. In fact, we're going to start to get into the definition of derivative today. But I guess I could just show you. If we were going to do it, it'd be power rule. Derivative of the top would be a 1/2, because that's a 1/2 power, right? Inside stays the same. Decrease the power by 1, but then you got to multiply by the derivative of what's inside, which would be 18x. Derivative of the bottom would be 1. We could clean this up. It's clearly not the easiest way to do this problem. We would get a 9x, because the 2 we reduce to 18, and then this would all be in the bottom inside of a square root because that's a negative exponent. And then if we were to plug infinity into this, we would get negative infinity over positive infinity. So I think this is probably bad because I think we're just going to go in circles here. I don't think it's going to lead anywhere, but you could try. Okay, so that was a warm up. Now let's talk about trig limits. This came up on, I think, the worksheet from the last assignment, but after today you'll have a much better idea. So plug in. If it's continuous, you just get the answer. Like this problem right here, if we plug it in, we get sine of pi over 3 over pi over 3. Sine of pi over 3 that's that bigger angle, 0, pi over 6, pi over 4, pi over 3, 0, 1/2, root 2 of 2, root 3 over 2, right? And then we can multiply by the reciprocal of the denominator, and the answer would be 3 root 3 over 2 pi. Okay? So fine, but what if it's not continuous? What do you do? Like in this case right here, sine of 0 is 0 over 0. Okay, and this is an indeterminate form, which for now we've been saying that's probably a hole in the graph. But here's the problem: we can't factor the hole out this time. So how do we deal with this? On a graphing calculator, I'll show you what happens, what this graph looks like. So we'll do, make sure I'm rating mode, sine x divided by x, and then window, I don't know, let's see. I'm going to go -1 to 2, -5 to 5. Let's try that. Oops, doesn't like my window. -5, 5. Y min is -1. Y max is 2. I mixed up. So here's a graph. And we could even, here, let's go -10 to 10. So it looks like a cosine curve, but getting smaller and smaller and smaller, right? So I mean, the graph looks like, and this value right here is 1. So it's kind of going like this, and it's going like this, and it's getting smaller and smaller and smaller. So I would say it has probably a horizontal asymptote. It looks like it's going to y equals 0 as time goes on, right? And then the value right there is 1. So we're trying to approach 0 from both sides. It's x equals 0. And it looks like the answer is going to be 1, right? I mean, it looks like the answer is going to be 1. Now let's see if I do calculate 0, there's a hole. There's a hole. We could do trace and be like, oh, okay, well, as we get closer and closer, x equals 0, y does appear to be getting closer and closer to 1. We could use a table, which I've shown you guys before, and say, okay, well, let's approach 0 from the right side. 0, 0.5, 0.1, 0.01, 0.001. And we can just plug 0 in there and see what happens. Error, because there's a hole. So, and I mean, if we were really trying to rely on this table, we would do it from both sides, but I'll save you guys the time and say, you know what, it's gonna do the same thing both sides. We can see it from the graph. And in fact, it looks like it actually got to 1 before 0, but watch out. Let's go highlight it. Oh, it's not really 1. It's the calculator rounds it to that 5th decimal place, and it, in this case, it ended up rounding it up to a solid 1. But this is what it really is. Okay, but you know, it appears to be going to 1, but there is a hole here in the graph, just like we've been experiencing. Now, here's the deal. In general, anytime you take h to 0 of sine of something over the same thing, it's going to go to 1. And I'm going to go ahead and let you guys just use that. Remember that. There's a couple other ways to prove it. It's interesting. In general, as values of x get close to 0, sine of x approaches the value of x, which is kind of weird. And that happens for sine. That's just for sine. So for small angles, sine of a small angle is actually almost equal to the small angle you're putting in it. So we're going to go ahead and use this result. Now, problem like this, I want to show you, it's not going to, usually it's not going to be so like simple. So like in this one, it's 2x. You'd be like, well, the idea here is that this is the same as this. These are the same, and they don't have to just be x. They could be 2x, but you're like, oh, but there's not a 2x here. Well, if there was a 2x here, guess what? The answer would be 1. Okay. Well, is there any way we could let ourselves just put a 2 times x right there? Sure, as long as we do it to the top. And so now this is going to go to 1, but then there's an extra 2 left, so the answer is going to be 2 times 1 is 2. So that's how we're going to do it. So we're going to actually use this rule in situations where it's not. Now, this next one right here, so we're forcing this pattern to occur, and we can, as long as we balance it out. So in this one right here, the first thing I would probably do is just kind of split it up. And, you know, and then what I would like to happen is I'd like a 3x to be here. Now, by the way, if you plug 0 into this, you get 0 over 0, and there is a hole in this graph. So I'd like to get a 3x here and a 2x here. Now, the x's that I need, they balance each other out. The extra 3, we need an extra 3. The extra 2, we need an extra 2, right? So now that's going to go to 1, that's going to go to 1, and there's a 3 and a 2 left over. Now, by the way, this idea works upside down, okay? So the final answer is going to be 3/2. This is the kind of work I want you to show. This is the shortcut, by the way, okay? Now, in general, I mean, okay, you could be like, and this is what some people think. They're like, on a problem like this, they're like, well, the signs cancel and the x's cancel, and so we're left with a over b. And then they check their answer, and they got it right. I'll call this the Charlie Chadwell rule, which I don't want you to use. Okay. Anyways, I mean, it's cool that it works. But anyways, I don't, this canceling of signs, okay, doesn't make sense mathematically, even if it happens to give you the right answer. And some of you guys, math find things that you think are patterns or it makes sense, and maybe they usually work out that way, but your logic doesn't make sense. Anyways, Charlie Chadwell was one of Mr. Statham's previous students, and his story is kind of interesting. He was kind of a slacker. He didn't graduate high school. Mr. Statham claimed he had a 0.25 GPA. Maybe he was in calculus, though. I guess he came up with this idea. He went to Quest. I think he did construction for a while. He went to Quest, and then he was able to get into UC Berkeley. Was a civil engineering major and ended up being valedictorian at UC Berkeley. And he received one of 12 full ride scholarships, got his master's, got his PhD, and then became a professor at Cal Poly. So even though his rule was flawed in logic and he didn't do great in high school, there's hope. You can turn it around. Sounded like a smart guy, though. You know, it wasn't that he wasn't smart. It's just that I guess he wasn't trying as hard at the beginning. I mean, if you can do all that other stuff later, that's pretty impressive. Okay, now L'Hopital's rule, which, why didn't we use L'Hopital's rule? Well, I think I've shown you this. We technically don't know the derivative of sine yet. I haven't technically shown it to you in a lesson. Now I think I used it on a couple of problems in the homework last night. So before we do that, let's talk about what the derivative of sine would be and cosine at the same time. Why not? So one way we could kind of sort of explore the derivative is to look at the graph, and we're going to start to do this more anyways. And let's see if we can try and sketch the derivative graph of a graph. Now, derivatives are just slopes, right? And so some of the easy slopes would be the ones that are flat, right? Those are zero slopes. And so those would correspond to a zero value on the derivative graph. This is going to be the y prime graph, right? And then we could kind of estimate, well, in this section, they're all positive slopes. And, that looks like it's about a slope of 1, which it's actually really close. And so we say, well, that's 1, positive. And here, it looks like it's like negative 1. Okay, and then here, it's probably like positive 1 again. Right? Okay, and then let's connect this with a smooth curve, because it's probably going to be like a smooth curve. So if we connect this with a smooth curve, and this graph is going to probably keep going, right? Does that look like any kind of function that you've ever studied before? What does it look like? It looks like cosine, doesn't it? Does that look like cosine curve? The derivative graph of sine looks like cosine. And so, in fact, that is actually what the derivative of sine is. It's just cosine. So kind of an interesting, not a very algebraic, proof or discovery of that. And the derivative of cosine, if we were to do it again, it would have zero slope here, here, and here. But then this would have a negative 1 slope, so it'd be down here, and then that would be a positive 1 slope. So the derivative of cosine, it looks like the sine curve, but upside down. It's going to be negative sine. Derivative of cosine is going to be negative sine. So coming back to this, now that we've proved it 0 to 0, and now that we can do L'Hopital's rule, then we can say, well, equals the limit as x approaches 0 of the derivative of the top. Derivative of sine is cosine. Derivative of x is 1. Cosine of 0 is 1. And that proves this rule that we kind of, looked at through tables and graphs. And so many different ways we've sorted it. But I'm totally in favor of you just using this as, now this only works if it's h going to 0, not infinity. Infinity you have to use like sandwich rule. Okay. Now, on to the back. You guys ready? We're going to start talking about derivatives even more, like how do we get these rules for derivatives? So now the derivative as a limit. So the derivative is the slope of a tangent line, right? Slope of a tangent line is the derivative curve. So here's a curve, and we want the slope here. And we draw a tangent line, and the slope of that line is the derivative. Okay, now, so how do we find that? Well, usually back, before when we find slopes in algebra and algebra 2, you needed 2 points to do rise over run. So what we could do is we could say, well, let's pick another point kind of nearby, and we'll say that's h away at x plus h. Okay, and let's find the slope between these 2 points and say that it's probably close to what we're looking for. Now, this is called a secant line, right? Back in geometry, you learned about secant lines, lines that cut a curve more than once. Tangent line only hits once. So h, by the way, for this small difference between the original, that's a common value that, books use and stuff, the AP exam uses. Now, to find the slope, we'd say, well, the coordinates here are x, fx would be the y value, right? This function y equals fx. This one would be x plus h, fx plus h. Okay, and so then if we were going to do the slope over here, the slope of the secant line would be rise over run f of x plus h minus f of x over x plus h minus x, right? And then that would become f of x plus h minus f of x. And you'll notice that the x's cancel each other out over h. And so this is the slope of the secant line. We're just doing rise over run. Now, sometimes we might write this as change in y over change in x. So this is a delta, which looks like a triangle. It's a Greek letter that is often used for change in math or physics or things like that. Now, here's the deal. That's a rough estimate for the slope of the secant line is a rough estimate for the slope. The slope of the tangent line is roughly approximated by the slope of the secant line. Okay. Now, how could we make it better? Okay. How could we make it better? We can move the 2 points closer to each other, because if I move this point to here and we draw that secant line, isn't that slope going to be better than the previous one? Isn't that one going to be closer to the one we're looking for? Yes. And if we move it even closer and we do that secant line, well, that one's going to be even better than the last one. And the closer and closer we move these points, the better and better and closer it gets to the actual answer. So closer and closer approximations are getting more accurate. Now, how do we write that? How do we show that? This is a limit idea. We're trying to get these as this approaches this. That's what we always say with limits. As this approaches this, or in other words, one of the things that's happening here is that h is getting smaller and smaller and smaller, right? So we're shrinking h down, going towards 0, right? So that would be the limit as h approaches 0, right, of this expression. This is still our slope of any secant line, right? And this, if we take this limit and we take h as close to 0 as we can get, our answer actually approaches the exact answer. It is no longer the approximation. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. This is the definition of the derivative. This part right here, that's called the difference quotient. The difference quotient. Quotient is fancy word fraction. Difference is subtraction. It's a fraction with subtraction. Rise over run, slope calculations, called difference quotient. This is the definition of the derivative. And all the derivative rules that we use and will memorize come from this basic, simple idea. And we could actually derive them, and we will derive some of them. So let's do one of them right now. So we're not going to drive the rule yet, but we're going to kind of see it worked out. So we're trying to take the, when you see this limit, what you need to realize in the future, and we've seen a couple of these on assignments, is that's not just any old limit. Like that's a derivative of something. Now, if you compare that to that, you should be like, oh, that looks like the definition of the derivative, right? And so what are we trying to take the derivative here? It's the f function with x plus h in it, and then x in it. So twice x plus h in it, and then x in it. Oh, that's y equals x cubed, right? I mean, that's what we're trying to take the derivative of, right? And so what should we get? We already know the rule. We've memorized this rule, the power rule. What's the derivative? It should be 3x squared when we're done, right? I mean, this is what we should get. So we already know what the answer is, but we're going to see if we can use this definition to get that answer. Now, x plus h to the third power, man, that's going to be annoying to expand. Expand means to multiply out, like FOIL it all out, okay? So we could use something called Pascal's triangle. And you guys should have probably seen this in Algebra 2. You may have blocked it out of your memory. I know people that I've even taught the next year and be like, no, we never saw that. I'm like, no, I'm pretty sure we saw it. Okay, it's this cool pattern that will actually make the work easier. So it's worth it. Even if it seems a little overwhelming at first, it makes work easier. Okay. X plus h to the third power isn't too bad. X plus h to the 10th power would be horrible to write out. And we need to for what we're trying to do right now. And Pascal's triangle is based off this idea that you have it's for a binomial expansion. Okay. Binomial expansion. Binomial is a two-term expression raised to a power, and then expansion multiplies it all out. So that's what we're trying to do here. Anything is 0 power is 1. So that's going to be 1. And so we're going to draw this Pascal's triangle here. It's kind of pyramid, this triangle of just numbers. A plus b to the first power is going to be 1a plus 1b. So the coefficients of the next terms are 1 and 1, right? A plus b squared is going to be 1a squared plus 2ab plus b squared. So the coefficients are going to be 1, 2, and 1, okay? Now, if we keep doing this, coefficients, the next ones are going to be 1, 3, 3, and 1, okay? The next ones are going to be 1, 4, 6, 4, 1, okay? Now, do we want to memorize these? No, but look at this cool pattern here. 1, all the first numbers end in 1, and all the last numbers end in 1, okay? The next number here is the sum of the numbers right above it. 1 plus 2 is 3. 1 plus 3 is 4. 2 plus 1 is 3. 3 plus 1 is 4. 3 plus 3 is 6. Okay? Right? And so there's this general pattern. We know that the nth one is going to start with a 1. And the next, there's a bunch of terms in here missing. The next term, the other thing you might realize is like the second term in every line is equal to the power. See that? Second term is always equal to power, unless it's the last term. The second term is always, so this is going to definitely be n, right? And we know the last number is going to be 1, and there's going to be a bunch of numbers in between. Okay. So there's a pattern here, though. Now, this is just for the numbers. This is just for the coefficients. Then you have to realize that it's going to be a to the first, a to the second, a to the third is going to be the first term. And then the next term is going to have a to the 1 power less and b to the next power up. And eventually it gets down to the a is going to be to the 0, and the b is going to be to the highest exponent that we start with. So here's how it works. We're going to say, all right, well, this equals the limit as h goes to 0, and we're going to use this row this time, okay? We're going to use that row for this one. We're going to say, okay, well, the first one's going to be 1 x to the third, h to the 0 if you want to write it, okay? And then the next term is going to be plus 3x squared h to the first. So you see how the power of the x goes down 1 and the h goes up 1? That's just a pattern. The next one is going to be 3 x to the first h squared. The next one's going to be 1 x to the 0. Now, once x gets to 0, you know you're at the last term, and then h is going to be back up to 3, which is what the x started with, okay? Now, don't forget that there's a minus x cubed here still, right? So we still got that all over h, okay? Now, by the way, when you plug h equals 0 in here, what do you get? You get 0 over 0. So it's a hole. It's an indeterminate form. There's a hole in it. And so we're going to see if we can factor out the hole. Now, we know the hole is at h, right? It's at h. And it's the only factor in the bottom. So on the top, look, this is x cubed, positive x cubed minus x cubed. And then we could factor out an h out of everything on the top, and then there would be a 3x squared plus 3xh plus h squared left. And that's the hole in the graph, and that goes away. And then we could reevaluate and plug h equals 0 into here, and those terms go away, and we have a 3x squared left, which is the answer. It totally worked, okay? Now, for this problem, what I want you to do in the future, most of the time, unless I tell you, on some problems I'm going to make you do it the long way, but most of the time, I want you to be like, hey, this is a derivative. And the function that we're taking the derivative of is x to the fourth. And the derivative of x to the fourth is 4x cubed. Done, okay? Done. AP test, okay? Now, I'm going to make you do it the long way on our next test. But after that, probably won't have to do it the long way anymore. But I want you to get at this. And I think on today's homework, there's probably going to be some that are a long way too. I'll show those. Okay. Now, let's talk about the power rule. Now, all we've done is shown that the derivative of x cubed is 3x squared. But could we show, the general rule that if you have a function x to the n power, then the derivative of that function is always going to be n times x to the n minus 1. That's the power rule. Okay, let's see if we could prove it. Okay, proof of the power rule. We're going to prove it by using the definition of the derivative. So we got to say, okay, well, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. We got to figure out what that is. Now, for this problem here, that's going to be the limit as h goes to 0 of x plus h to the nth power minus x to the nth power over h, right? And we're going to plug x plus h into our function and x in our function. And then we need to, now we kind of got to do like Pascal's triangle here. But the problem is we don't know what the power is, okay? What we're going to do, though, is we're going to say, okay, well, it's the nth power, so let's use the nth row. And we know at least the first term is going to be 1 times x to the nth h to the 0, right? Plus, we know the next term is going to be n times x to the n minus 1 h to the first, right? After that, I don't know what the numbers are going to be. It depends on what power it is. The thing you do know is that for sure, all the following terms at least have h squared in them, right? Because it's going h to 0, h to 1, h squared, h cubed, h to the fourth, all the way up. All the rest of terms have h squared in, right? So there's a bunch of stuff, a bunch more terms. Who knows? But we know we could factor in h squared, right? Right? The rest of terms at least have h squared. Now, we still have this minus x to the n right here, right? So don't forget that. And it's all over h. Now, here's the deal. That this term right here is going to cancel that term, x to the n. H to 0 is just 1, right? So that's positive 1x to the n minus x to the n, those cancel out. We know that we're trying to get a whole out of the graph, factor an h out. So we know, look, all the rest of the terms have an h, right? This one would be n x to the n minus 1 left. We would factor 1h out of all these and leave h the first times a bunch of stuff, whatever it is. I'm just leaving it. And the truth is we don't really need to know that. I'll show you in a second. Cancel out the whole, right? Plug h equals 0 in. Now, if h equals 0, this is h. Don't confuse that with the n. Then that's going to go here, and that's all going to go away. And guess what's left? N x to the n minus 1. We just proved it. We just proved. Now, every rule starts at the definition of the derivative, okay? Now, your calculator, by the way, doesn't know the derivative rules. It doesn't calculate them exactly because it would take infinity for it to keep trying to get h closer to 0 in practicality. So what it does is, you have a graph here, and let's say you want the slope at 2. It says, okay, we're gonna just do the slope of a secant line. It just does slopes of secant lines, but h is really small. It's 0.001. So this is gonna be at 2.001, and this one's gonna be at 1.999. And so it does that calculation. Okay, so these are the values that your calculator would have. If we did a little quick table in your calculator with this function, I think I'm doing a y equals x cubed right here. And so this is how your calculator does it. It's not going to show you all this stuff, but it says, okay, well, 8.012006001 minus 7.988005999 over 2.001 minus 1.999. And so then it gets 0.024000002 over 0.002. And it gets 12.000001, which is pretty good. Now, this would be the derivative at 2, which the exact answer would be 12, right? It's not perfect, but it's pretty close. Now, by the way, it uses a symmetric difference quotient. So there's actually different versions of different quotient. We used a right-sided difference quotient. We took the point and a point to the right that we kept scooting. But you could take a point on the left and the right instead and say, okay, well, let's do f of x plus h minus f of x minus h. So we're going to go h to the right and h to the left, and then the denominator would end up being 2h. So this is a symmetric difference quotient. They also have a left-sided difference quotient. So I'll show you that one right now too, because you're going to see these pop up. The right-sided one's the most common. Now, if you're going to go a point and the point to the left, then you probably do f of x minus f of x minus h over h. So that would be a point and then a point to the left, x minus h. We'd probably do that second, so that we did bigger minus smaller and didn't get like a negative on the bottom. This would be a left-sided difference quotient. Okay, now let's look at the homework and on the worksheet, and I'm going to help you guys out on a couple problems right now. Okay, so on the homework, assignment 4, let's flip. So this is assignment 4. I'm going to flip it over and give you guys a little bit of help on the back. Okay, first. So we're going to look at 20 and 29. I'm going to try and give you guys a little help. Okay, and also to help you understand what I want you to do. So in 20, so we're going to do 20 and 29. So on problems 20 to 23, it says symmetric differences. Use this to find the derivative. So these ones I don't want you to do the lazy way. In the future we will. So we're going to use the symmetric difference quotient this time. I could ask you to use the symmetric, the right one, but you're just going to essentially. Now, the first step you're going to do to find the derivative is you're going to just go ahead and plug x plus h into this, right? X plus h cubed plus 1, okay, minus x minus h cubed plus 1. Now, I'd put the whole thing in parentheses because we're going to have to distribute this subtraction all over 2h, okay? Now, the next thing you got to do is you got to expand this. So this is where Pascal's triangle is going to come in handy. So I would do Pascal's triangle real quick. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, right? This is 0th power, first power, second power, third power, fourth power. So we want the third power. And so then that's going to be 1 times x to the third, h to the 0, plus 3x squared, h to the first, right? So the the first one starts at the highest power, the second one starts at the lowest power. And then the first one goes down in power by 1 each time, and the second one goes up in power by 1 each time. Plus 3x to the first, h squared, plus 1 x to the 0, h cubed, okay? Plus 1. There's a plus 1 there. Okay. And then minus, that's the whole first one. The next one is going to be 1x. Now, be careful here because this h has a negative in front of it. So it's going to be 1x to the third negative h to the 0. So the negative has to be part of it. Okay. Plus 3x squared negative h to the first plus 3x cubed negative h to the second plus 1x, sorry, it should be x to the first, x to the 0, negative h to the third, and then there's another plus 1 there. Okay, so this is kind of messy. I want you to do this. We're not going to do that many of them. And then it's of course, all over 2h. Now, we got to try and simplify this. This is going to be positive 1, okay? This is going to have a negative from it, but we're also distributing negatives, right? So there's a x cubed minus x cubed, so those cancel each other out. There's a 3x squared h minus negative 3x squared plus h. So those actually add up, 6x squared plus h, because a negative times a negative. Then there's 3x h squared minus 3x squared, 3h squared, so those cancel each other out. And then there's the xh cubed minus negative h cubed, so there's going to be a plus 2h cubed, and then there's a 1 and a minus 1. Those cancel each other out, all over 2h. So this is what we have, okay? And we should do the limit also, by the way. Limit as h goes to 0. You should write that in your work. I need that in your work, your next test. So I'm going to make you do one of these in your next test. So this is your opportunity to start to get good at it. Now, of course, if you plug 0 in, you get 0 over 0. And so we're going to factor the whole out. And so we're going to take an h out of everything, right? I would just take the h. And then you have 6x squared plus 2h squared over h, over 2h, because it's symmetric. Now that's the whole. You plug 0 back in, this term goes away. There's still 2 on the bottom, so it gives you 3x squared. Now, by the way, you should know what the answer to the derivative of x cubed plus 1 is going to be. What is it? 3x squared. So you're going to know if you got it right or not. Okay? Maybe not so much on 22, but anyways, try these problems. Okay? I guarantee you need practice with them before you have to do one on a test on your own. Okay? But I just did one of them for you. Now, down here on the last chunk of problems, I want you to use your knowledge of the definition of derivative and the power rule to get these answers. So in other words, these ones I want you to do the quick way. I want you to be like, oh, this is a derivative, right, of what function? Now, if you see a number, this is usually where the x is, right? If you see a number where the x is, just ignore that for a second. Just say, okay, well, that would be x cubed, right? And the derivative of x cubed is 3x squared. And if there were x's, you would be done. But when there's a number there, what that means is after you find the derivative, go ahead and evaluate the derivative at that point. Okay, so if they have x's like 27, 28, your answers are just going to be the derivative of x. But 31 and 29, you see these numbers where the x's usually would go, right? And that means imagine there's x's there, but then plug that number in after you're done. Okay, try this worksheet. We're starting to really get in some good calculus stuff now.